that, we are very pleased to start with our first team. And I am now going to hand the floor over to Hannah and Jennifer from the University of Colorado to take it away. Hannah and Jennifer, the floor is yours.
Hi, everyone. Thank you for being here. I am Hannah Blake, and I was the co-leader of the University of Colorado Boulder Solar Decathlon team who designed and built the SPARC House. The SPARC House is designed for real people in a real town called Fraser, Colorado, which is one of the coldest places in the lower 48 states. Designing an efficient all-electric house in one of the coldest climates in the US allows our team to set a precedent for sustainable housing. The 5 pillars that represent the SPARC House design philosophy are sustainability, performance, attainability, resilience, and community. As we walk you through the house, you'll see how these elements come into play. We decided to focus on the concerns for communities in our state. Mountain towns are seeing an attainable housing shortage that is displacing seasonal workers and middle-class families, both of which are vital components of these local economies. Many of us visit these ski towns on vacation during the on-season, but what happens during the off-season? There are people who live in these towns full-time to keep them running, and they're too often overlooked. Because of the cold climates, the build season is short, and with a skilled labor shortage, the focus of development has understandably shifted to high-return luxury second homes. Additionally, building materials are often less accessible to more remote mountain town locations. These factors together drive land and property prices up and push more people out. Our solution to confronting these issues is threefold. The first is the rental unit, one of the most unique elements of our house. This is an attached lock-off space that homeowners can rent out to seasonal workers in their community. Second, you're going to see a number of systems integrated into the home that balance its livability with efficiency to keep occupants safe, comfortable, and healthy. The third strategy we used was prefabricated panelized construction. We partnered with a local company, Simple Homes, who fabricates house panels in a climate-controlled warehouse in Denver. We constructed highly insulative and durable wall panels that have multiple layers of Havelock wool insulation and weather and vapor barriers that could be assembled on site. We built the wall panels at the Simple Homes warehouse in Denver a year ago, and they were set on site by Simple Homes in just 2 days this past fall. The prefabricated panel approach helps address affordability, a short build season, and mountain town labor shortages. In the next couple of slides, you'll be able to see the part of the house that's the rental unit and which part of the house is the main unit. The main unit on the right is the 2-story portion, and we have our rental unit as the 1-story portion on the left. And now we will begin our tour to showcase the SPARC House, our team's net zero all-electric home suited for the coldest place in the lower 48. Each elevation is made from separate prefabricated wall panels. The panels are connected together by structural ties, a weather barrier, continuous insulation, and pine tar siding set on furring strips to create a rain screen. A unique aspect of our house is that it's 2 stories. A multi-story house can fit more living space on smaller plots of land, which is an expensive resource in mountain towns. It also allows for separation of interior space, so there still can be a clear distinction between shared and private areas. Other benefits of a 2-story house is that in general, there's better access to daylight, views, and natural ventilation. Also, solar panel production is less affected by shading from trees. The 2 main roof pitches face southeast to increase production from the 7.6 kilowatt solar system on the roof. And to increase energy efficiency, the exterior walls are over 1 foot in thickness. In addition to the continuous mineral wool insulation behind the pine siding, there is also sheep's wool in the 2x8 framing structure, creating a highly insulated envelope for the home. The Alpine windows are strategically placed, and they're quad pane, meaning there are 3 gas-filled gaps within the overall window for high thermal performance. The roof is standing seam metal, which is a durable material, an important consideration for the harsh Fraser winters. And the pine tar coating on the beetle kill is highlighting a piece of mountain town history, being that pine tar was the earliest known wood preservative applied on skis to prevent water absorption. the house has 3 Mitsubishi single-zone cold climate heat pumps to heat and cool the home. A single-zone system reduces standby energy losses because only the zones that are being used will need to have hot air running to them. So our team was able to size the units for maximum efficiency. Cold climate heat pumps are a newer tech offering that are successful by using a flash injection circuit, which cools the compressor and uses the waste heat to help heat the house. The inverter-based variable speed compressors are able to provide about 1.5 to 5 times the heating capacity compared to the amount of electricity used, even in extremely cold temperatures. Using this door on the right, renters will enter the home through their own private entrance. The rental unit allows the homeowners to support their community by renting out the space to seasonal workers who are in need of affordable housing, thereby also receiving a source of income that can be used to offset the main homeowner's mortgage cost. This space also provides flexibility because homeowners can grow into their home and decide to use the space for other reasons whenever they choose to. This unit is designed as a studio space with its own kitchenette, beautiful sweeping views of the surrounding mountain ranges, and plenty of daylighting. Now we'll head over to the mechanical closet. We designed and built our house to be airtight, meaning it has very little air leakage at window and wall penetrations. The Renew Air energy recovery ventilator on the ceiling allows us to introduce the right amount of fresh air as needed. This device brings in fresh air from the outside and exhausts stale air from the house. And as the streams of air pass over a heat exchanger, the indoor air is warmed using the waste heat from the exhaust air. We have an electric water heater for its ability to store thermal energy, and the SPARC house can participate in utility demand response programs or align water heating with solar panel electricity production because we have a tank on the water heater. We also have an energy meter which has already shown us that the SPARC house is producing more energy than it consumes for a typical mid-year day, even as temperatures are below freezing. This mechanical room is one potential location for energy storage. Our house is resilient ready, meaning that it is designed for the addition of a 16 kilowatt hour modular battery system. As we go back towards the rental unit main kitchenette space, let's note the electric lighting fixtures. The design intent for downlights in a soffit and the use of sconces is because we prevented all unnecessary air penetrations in the air barrier, which sits just behind an electrical chase. Now we'll enter the main unit. On this level, you'll see the open living space and full kitchen with high efficiency Energy Star Beko appliances. An important design strategy we wanted to uphold is the use of a wet core. So we kept all the plumbing systems as close as possible to the central demising wall between the units to limit the length of hot water and duct runs. Under the stairs, there's a reading nook, and to the left of that, there is a half bath so that guests don't have to enter the private main bedroom area upstairs to use the restroom. There's a 4-foot plus crawl space underneath the house that spans the entire footprint, which is a great place for storage, including winter gear storage. As we go upstairs, you'll notice one of the 3 indoor heat pump units, and immediately when you reach the second floor, you're in a flexible space that we have designated as an open office space for the homeowners. There's a type of high set window above the office space that is along the south facing wall, and that window appears 3 times along that south wall and only 1 time at the north facing wall. These windows are operable, so they're great for passive cooling in the swing seasons and during summer nights, and contribute to the passive heating of the home during the winter with south sun exposure. An added advantage is that the height allows them to perfectly capture the scenic mountain views without including all of the immediate neighboring houses. This detail provides a sense of seclusion while also better protecting the homeowner's privacy upstairs. Over next to the bedroom on the second floor, we have a stacked washer and dryer. It's a heat pump dryer, which means there's no need for vent penetration through the house's envelope. And then once we enter the main bedroom, you'll see that there's a lot of natural light from a combination of windows and mirrors. From the window above the main bedroom, our clients, Kristen and Joe, have shared that during the day, they can see the Continental Divide, and at night, they can see the stars right from the comfort of their bed. We hear it's their dream come true to live in a house that connects them with the mountains while addressing our current climate crises that require us to protect these environments that we care about. Most importantly, this house represents a viable, sustainable option for a lot of people. The all-in costs are roughly $440,000 for 2 new living options in Fraser, Colorado, with rental income estimated at $800 per month. Thank you all for listening. I appreciate it, and I hope you enjoyed our tour.
Great, thank you very much for that presentation. We really appreciate it. It's an impressive house, and now we understand why you are one of the winners. And so with that, we will ask you to, while that presentation is fresh in your mind, chat in your questions, and we will keep those till the end after the last team. And we will cull from the questions that have been submitted at that time. But again, it's always best we find to think about them while this presentation has just been given. And we are now going to move on to our next set of presenters. And we have already done the introduction, so you are familiar with who you're going to hear from. And so we're going to turn things over now to Northwestern University to talk about their winning work in the solar decathlon. Northwestern, the floor is yours.
Hello, we are Ingenuity from Northwestern University, and this is New Home. New Home is located in Chicago, Illinois, the 3rd most populous city in the US. Chicago has a long history of dense urbanization. In October of 1871, the Great Chicago Fire destroyed a third of the city, providing city planners with a clean slate to design a more efficient street layout. This new standard arrangement gave rise to Chicago's now typical narrow lots. In the early 20th century, as the city grew, the iconic two-flat home design was developed in response to the demand for workforce housing. Today, developmental pressures, disinvestment, and changing values are diminishing the stock of affordable housing options near the heart of the city. Additionally, rising CO2 emissions, energy usage, and resource waste are leading to harmful environmental degradation on a global scale. To combat these issues, the city of Chicago is in need of more affordable and more sustainable housing options. The site for our building is located in Lakeview, a few miles north of the heart of downtown. It has easy access to many forms of public transportation, such as trains, buses, and bike sharing. The building lot is a narrow strip of land, 25 feet wide and 125 feet long, with a side street to the north, an alley to the south, and 3-story homes on both of its long sides. The site's narrow footprint constrains the space for building, and its proximity to neighboring buildings makes solar access more difficult. Furthermore, Chicago's harsh winters and hot summers makes it difficult to balance residential energy production with residential energy consumption. Finally, the higher upfront cost of sustainable construction is often a large barrier to the implementation of more sustainable homes. To design a home suitable for this context, the goal of New Home is marketable sustainability. To be competitive in a market, a home must address the buyer's main concerns of financial feasibility and healthy living. And to be a sustainable home, it should emphasize resiliency and versatility and environmental consciousness. Our approach to making the home market ready is efficient construction and future-proof design, providing open living, natural light, and bringing nature indoors. The sustainable design focuses on being family responsive, ensuring durability, providing diverse housing options, reducing consumption, and strengthening the neighborhood. New Home is approximately 2,300 square feet, with a main home on the 2nd and 3rd floors of about 1,800 square feet, featuring 2 beds and 2.5 baths. An accessory dwelling unit takes up a large portion of the 1st floor, providing a self-contained living unit with 1 bed and 1 bath. The home's 11.3 kilowatt solar roof, high-efficiency HVAC system, tight thermal envelope, gray water reuse, and other sustainable features give the home an ERI rating of 12 and a HERS score of -22.
Large windows on the southern portion of the home provide plenty of natural light for the main living spaces. The ADU's ramp entrance, open floor plan, sliding doors, and ADA accessible bathroom ensure comfortable living for all levels of ability. Sliding walls allow flexibility in the purpose of the ADU, from an income unit to an in-law suite to even a quarantine living space. A double-high living space in the main home feels large and welcoming while providing plenty of natural light for the living room and centrally located kitchen. A moss wall across from the kitchen offers a unique natural focal piece while purifying the air and reducing noise. A skylight above the dining area provides natural light deeper into the home, brightening up the spaces for improvements in productivity and mood. The master bedroom features a large walk-in closet and private full bathroom, and the secondary bedroom also has its own full bath, featuring a smaller corner shower. A small work den on the third floor provides comfortable working space with natural light, and another workspace on the first floor, which maintains separation from the rest of the home through a staircase and a lock-off, can be easily converted into an office or studio for a small business. For the overall building shape, several options were considered. The basic box maximizes square footage with the smallest envelope. A first floor ADU reduces the energy lost in heating and cooling the space and provides easy access for all levels of ability. Finally, a south sloping roof maximizes the solar potential for making this a net zero home. The roof itself, coupled with a balcony, optimizes sun angles, allowing us to minimize heat gain in the summer and maximize heat gain in the winter through the south-facing windows. To maintain a tight thermal envelope, we chose a 2x4 double stud approach, using both EPS and dense packed cellulose insulation, as well as a frost-protected shallow foundation. This type of foundation saves on excavation and labor costs and takes advantage of the home's heat losses, as well as geothermal heat, to raise the frost depth around the home. A minimal concrete approach using a structural fill and 6 inches of EPS slab ensures structural integrity while increasing thermal performance and lowering concrete use. For the main superstructure, a double stud approach allows for straightforward construction, use of common materials, low embodied carbon, and integrated space for our dense packed cellulose insulation. Designed such that the roof bears on the outer walls while the floors bear entirely on the inner walls, the framing method maximizes the depth of continuous insulation and eliminates thermal bridging at the rim joist. To minimize material waste and construction time, the frame was designed such that it can be broken down into several prefabricated sections. A Class 3 vapor barrier behind the interior gypsum board finish provides protection from adverse moisture conditions, and liquid weather wrap below the exterior cladding provides seamless protection from the elements. At the roof, a combination of dense packed cellulose insulation between trusses and a continuous layer of EPS insulation above the roof sheathing completes the tight thermal envelope.
Building off of that, the water system of New Home is specially designed to maximize ease of construction and occupant comfort while minimizing water use. This is reflected by our water core design, in which all of the pipes and water fixtures in the home are centralized within the same interior wall of the building. WaterSense low-flow fixtures and Energy Star water appliances were incorporated into the water core, as were user-friendly manifolds and gray water systems. 65% of flush fixture water and 16% of landscaping water in New Home is offset by gray water. This, combined with New Home's efficient fixture selection and landscaping design, results in a dramatic 60.5% overall potable water use reduction, translating to a 60-year saving of more than $34,000, making this home environmentally and financially sustainable. New Home's key energy saving features are a super insulated and airtight envelope, heat pump heating, cooling, and water heating, energy recovery from ventilation and drain water, and the most efficient and ADA compliant appliances available. This brings our EUI from 39 down to just 12 and brings our HER score without PV from 100 to just 31. With 11.3 kilowatt of PV connected to microinverters for extra resilience, we generate 14 megawatt hours of electricity and bring our HER score down to negative 22. Even if New Home's family chooses not to purchase a residential battery, New Home will function off-grid for 65% of daytime hours and reduces load on the grid during peak times by 43%.
On an annual basis, a typical home of this size in Chicago would cost just over $6,000 per year. New Home, on the other hand, because of its energy efficiency and PV capabilities, costs just less than $3,400 per year. Taking this a step further, we can see that over a longer period of time, in this case 60 years, with the ADU being rented at an affordable housing rate for half of that time, the net cost of New Home is nearly $475,000 less than the net cost of a typical Chicago home of the same size, thus making this a very financially feasible alternative to minimally code-compliant construction.
As a result, New Home offers a perfect solution to aging in place in Chicago. Ria and Enzo just bought New Home and have rented out the ADU using the income to help cover their mortgage. Once Ria and Enzo have a child named Shreya, the ADU transforms into an in-law suite so Ria's parents can help raise her. When Shreya gets older, Ria and Enzo rent out the ADU again. And as empty nesters, Ria and Enzo move into the ADU, allowing them to downsize their living space while staying in their community. New Home reimagines modern living in Chicago by providing a healthy and functional home with maximum efficiency in its layout and envelope, decreasing daily impact through water use reduction and net zero energy usage, and using common construction practices with the adaptable ADU to help offset the cost of the home's sustainable features. New Home focuses on marketable sustainability because for something to be sustainable, it must first be attainable. We believe the future of new homes is New Home.
Okay, thank you very much for that extremely informative and well-paced presentation by the Northwestern team. Very impressive, and again, it is quite clear why we have them as one of the winning teams with us today, sharing their good work. And so again, while their presentation is fresh in your mind, now is the time to chat in the questions you want answers to, so we have those in hand when we get to the question and answer session after the final team. But once again, thank you very much to the Northwestern team for a stellar presentation. And we are going to come back to all the teams again in a little bit for a vibrant discussion about their work. But thank you. And we're now going to move on to our next and final team. And we are going to turn the virtual keys of the car over to the University of Oregon to share their work in the 2021 Solar Decathlon. And so with that, it gives me great pleasure to turn the floor over to them. University of Oregon, you're up.
Thank you. Hi, we are Team Riparian from the University of Oregon, and we are the Grand Jury Award winners for the commercial division of the 2021 Solar Decathlon. This is our project, the Martin Luther King Jr. Montessori Elementary School. My name is Lauren Bennett, and I am a first-year Master of Architecture student.
My name is Jared Levy. I'm in my third year of my B.Arch.
And I'm Kyle White. I'm in my first year of the Master of Architecture program. Our faculty advisor and professor was Ziha Belziadi.
Approaching the project, we first analyzed the site and climate of the existing school in the King neighborhood of Portland, Oregon. Through this analysis, we decided to approach the project from a bioclimatic design strategy. It takes advantage of diurnal night-to-day swings and maximizes passive climate control of our building.
Through a series of community interviews, we learned that much of the public thinks the existing school is prison-like and institutional compared to the surrounding residential neighborhood. In response to their concerns, we wanted to create a school that strengthens the roots of this marginalized community and addresses social, economic, and environmental sustainability.
Our analysis led us to a series of questions. How can our school strengthen an underserved neighborhood, serve as a third teacher, and provide a positive life cycle impact? Current test scores are low, which made us ask, what about the existing building is failing students? The team shifted curriculum to the Montessori method, which connects existing community issues like poor academic performance and lack of community engagement with the proposed sustainable interventions.
Ultimately, 5 goals were used to guide the design process. These goals helped the team ensure that our school would act as a resource for the community and influence architectural scale, materiality, and program. We wanted to emphasize and celebrate net zero systems by making them visible throughout the entire project.
The existing school is massive in comparison to its residential context and has minimal green spaces or separation from the road. Breaking down the mass into 3 separate structures creates ample daylighting opportunities, plentiful outdoor areas, and a building form that relates to the surrounding context.
The site has 4 educational landscape zones, which act as natural access control and reintroduce native habitats into this urban context. The southernmost building can be operated year-round after hours to host community events. The northern 2 buildings are the classroom neighborhoods. Each one has 6 classrooms, a collaboration space, and direct access to outdoor learning opportunities.
As Montessori curriculums typically have students prepare their own meals, our cafeteria has a prep station that can accommodate both adults and children. Flexible furniture and overhead doors allow our gym and cafeteria to be combined for large gatherings. The passive design of these spaces enable these spaces to be used during off hours and weekends.
As a passive 2-story space, the library is inspired by storytelling. Mobile and adjustable furniture creates a dynamic space for group work and individual learning. Large sliding doors and north-facing skylights bring nature inside, and a central elevator ensures that our project is accessible for all.
The STEAM area contains a makerspace, computer lab, and discovery deck. These hands-on learning areas introduce students to the detailed mechanics of things like photovoltaics and water harvesting.
Our outdoor spaces create engaging learning opportunities about the environment and sustainable living. They're filled with regional habitats, bioswales, and interactive play areas that connect directly to the classrooms.
The classroom buildings are organized into 2 separate neighborhoods. By splitting the student body into smaller groups, students can form stronger bonds and friendships with each other. Each neighborhood also features a common collaboration space, which is passively conditioned for small group learning.
Classrooms are structured around the Montessori pedagogy of teaching. Featuring a classroom kitchenette, expansive storage, and cubbies, the open floor plan maximizes flexibility and allows for students to redesign their environment as needed.
The building utilizes mass timber construction with cross-laminated and dowel-laminated wood panels. Conventional wood framing and a thermally efficient envelope created a financially accessible and durable construction.
The team created a zoned approach for the school's thermal design based on program and duration of occupancy. We have active, passive, and hybrid spaces.
The active mechanical system for the public portion of the building is designed as one central air handler unit. Distributed through a series of insulated spiral ducts and VAVs, the gym, cafeteria, and kitchen are zoned separately. The return air is fed through a central energy recovery ventilator, further reducing energy consumption.
Designed to have students participate and manage the thermal comfort, passive design includes operable windows, ceiling fans, strategic thermal masts, and solar chimneys. All these systems are on display for the students in the library, furthering their exposure and responsible management of their environment.
In the hybrid approach to climate control, students are encouraged to use passive design elements augmented with smart controls to condition the space. Additionally, to moderate the climate of the room more consistently, radiant floor heating and exposed chilled beams are provided.
Breaking up the project into multiple buildings also created opportunity for a phased approach of construction, providing ample space to support and maintain the student body of the school.
The team evaluated the life cycle analysis of the building. Using recycled materials and increasing the biogenic carbon storage through wood construction, the project resulted with a significantly reduced global warming impact compared to a steel or concrete building. Using locally sourced materials and reducing the mechanical systems in the project brought the overall construction estimate to $220 per square foot. Additionally, lower running maintenance costs and energy bills would create funding for community-based programs and teacher benefits.
Active insulation panels enable students to explore thermal comfort while boosting envelope efficiency. The insulative screening system consists of sun screening shutters that, when layered, create additional thermal resistance. Also, this system aids in preserving heat trapped in the thermal masses after collection hours.
Solar chimneys were implemented in the school's passive spaces. Vertical shafts utilize solar radiation to heat the air and create a convective air current. Warm air is vented out through the shaft and cool air is sucked in through open windows and vents.
Cyclical energy modeling and simulation enriched the design process of the school and ensured the reciprocity between the architectural design and energy performance. Efficient energy use and on-site PV generation allowed the project to move into the net positive range.
Providing daylighting autonomy was at the top of our design priorities due to its proven impacts on students' academic and physical performance. We evaluated our roof geometry, and solar shading optimized east-west gables for both solar and rainwater harvesting. As a result, a moderate-sized photovoltaic array was able to meet our energy demands and even produce excess energy to send back to the grid.
Our rainwater collection and gray water recycling systems are estimated to reduce city water consumption by over 90%. On-site bioswales also help support the natural habitat and provide a learning opportunity for students.
Martin Luther King Jr. Elementary School aimed to strengthen the marginalized community of our Portland neighborhood while re-engaging students through hands-on learning, environmental responsibility, and neighborhood connection. We feel that these qualities, in addition to our net positive status, are what made the project a success.
This was a wonderful experience, and we all gained really valuable insights to the world of net zero design. Thank you all very much.
Thank you very much. We really appreciate that presentation, and we have now gotten a better idea about why you two are a winning team in this year's Solar Decathlon. So fantastic work, all involved, and we want to say thank you to each of our teams. And again, while this presentation is fresh in your mind, please do chat in questions. You have the functionality on your screen. You can also raise your hand virtually, because we are now going to move into the Q&A section of our program that will take us out through the final third of this hour-long session. And we have lots to ask about after those three presentations. And I think the future of the clean energy profession is in much better hands with these three teams. So thank you again for those extremely intelligent, articulate, and well-presented efforts. So with that, I'm actually going to turn things over to my colleague Tyler, who is combing the chat box for questions for each of the teams. Tyler, what do we have over the line for our three participating teams today?
Well, among the many questions, we also have a lot of interest in getting a recording of today's presentation. First, I just want to note that we will be sending an email to everyone with us today containing a link to the website, which includes or will include this recording as soon as we post it in the next day or two, as well as all of the other Florida Decathlon virtual sessions that we've conducted over the last year. So just wanted to let people know that. And then getting into the questions proper, let's see. Does the Colorado University home have any rainwater collection or gray water reuse options?
Can you hear me?
Yes.
Yes, we can.
Oh, great. Jennifer, you popped in if you want to get that one?
Oh, sure. I didn't know if you heard the question, but the answer is pretty simple. No, we did not include any rainwater capture due to Colorado laws, and also not a focus for us in this particular project.
All right, thank you for that. Also for Colorado, Casey asked if it is hard to find affordable land to build on when developers are trying to maximize profits on the already expensive land, specifically in Fraser, Colorado.
Yeah, that's a really good question. Our homeowners, their site was kind of like an oblong, really skinny trapezoidal shape in a neighborhood that was already existing. So that just kind of is a good representation of how a lot of these neighborhoods and mountain towns have small, oddly shaped plots of land that aren't necessarily the first choice for developers building big mansions and second home vacation rentals. So there is definitely kind of a market for small and more normally shaped plots of lands in existing neighborhoods.
Very good point. Thank you. Did any of the teams do or consider an embodied carbon analysis?
I can hop in. So for our project, we had an existing building that was obviously a hard decision sustainably to either remove or renovate that building. So we did perform in our LCA an embodied carbon analysis, and we essentially had to justify the loss and the waste of that embodied energy with our new construction. And so we put significant effort into being really minimizing our footprint and minimizing the greenhouse gas collections in our LCAs. And that's how we ended up creating our new construction, which achieved a bunch of new learning goals, but also justifying the demolition of an existing building.
So I can speak for the Northwestern team. We did do an LCA with our one-click LCA software, and we didn't include this in the presentation for the sake of time, but we ended up getting that like our materials for our building resulted in like an embodied carbon of like 21 kilograms of CO2 per square foot, which was actually less than the biogenic carbon storage that we had because we used a lot of wood as well as like recycled materials and stuff with our cellulose insulation and like our reclaimed wood siding and like recycled glass countertops, among other features. So yeah, it was definitely something that we considered in our design.
Great, thank you.
I can round out the, for the third team, I'll speak for Colorado. We didn't do a formal analysis, but just the idea was sort of our guiding approach to make decisions like using wool over foam insulation products, use of beetle-killed pine where we could, trying to use two-story design to minimize materials and little use of concrete. So we just went that direction in our material choices.
Thank you to all three teams. We had a lot of questions about the solar chimney at the school in Chicago. So I think this one is probably representative. Ellen asked, what is a solar chimney in the school? Are there more details on how that functions or that show how it functions?
I can speak briefly on the solar chimney if you want. Basically, the solar chimney is what you would think of as it's just a chimney that its southern face is exposed to, has a glazing panel that allows the sun to superheat the air within that chamber. And that warm air then rises out of the chimney, pulling air down in through the bottom. So it helps to ventilate, but it can also help to cool the building by taking the warm air out of the building and pulling in cool air from places where you can have specific microclimates like bioswales, like we incorporated, that can help cool that air and bring it in through the building.
Thank you for that additional insight or context, rather. And I guess also about the school, we had a few questions asking, has the school been built? Is there any chance that the school might be built? What has been the reaction of the city and school system?
I can take a stab at this one. So the project is not a proposed project in reality. We have been working with the staff of the Portland School District, who have come to a series of our reviews and have given comments. They really enjoyed all the concepts and the change in pedagogy that we've put forward. Unfortunately, we don't know if they'll move forward. The existing building is on it's on their projects list, I think, in the next 10 years. So hopefully they can take some inspiration from our proposal and move forward with some of those ideas.
Certainly. Well, thank you for that. Going back to Colorado, a couple of questions about appliances. Judith had asked if you could provide more details about the hot water tank and how it works. And another gentleman asked if you would explain how the clothes dryer does not require an exhaust duct.
Sure, I can respond. I think the first question was about the appliances, the water heater. So it's a tanked electric water heater instead of a heat pump water heater or instantaneous. And so it works like a typical electric resistance tank. But I think probably the feature you're asking about is how does it participate in demand response? And that is through a separate relay attached to the top of the system. And it can be controlled, it's called SkyCentrix, and it can be controlled directly from the utility if there's a utility program, or we connected ours through Home Assistant. So it could be controlled through the home's Wi-Fi, and it can be controlled in a number of ways, pre-scheduled. It can just reduce the demand, or it can completely shut off the unit. So that is how that works, and I'd be happy, maybe I didn't quite hit the nail on the head with that question, or that answer, let me know if so. And then the other question is about the heat pump dryer, I believe.
if you could explain how the clothes dryer does not require an exhaust duct.
Right, and so the way that works is the water is just condensed and then drained out below the dryer. And so you're not trying to exhaust out the back as we would have otherwise.
Oh, okay. And while we are on the Colorado House, I don't know if this is maybe just a comment, but if you have thoughts, please feel free to share them. Alan had noted that that this house is much larger than previous solar decathlon designs. So I don't know if there's some opportunity to further explicate something, a concept or a direction that you think is notable, or if that's just something that was coincidental.
Yeah, I can comment on that. So the total square footage is just under 1,200 square feet. And we made a lot of design decisions to make the home feel larger than it actually is, like higher ceilings. The ceilings in the main unit are about 9 feet high, and in the upstairs portion of the main unit, about 8.5 feet high, and same with the ADU. It's the lowest part of the ceiling in there is 8.5 feet as well. So just a little bit taller than average ceilings. And also the floor boxes are 28 by 14 feet, and there's 2 that sit on the ground and then 1 that composes that second floor portion of the home. So because it's kind of that elongated floor plan, we tried to accentuate that with the beetle kill ceiling that goes lengthwise along the space to kind of draw your eye through the space. So yeah, so with the just under 1,200 square feet and 2/3 of that being the primary living space for most of the year, it's modest, but definitely not the smallest house ever.
Yeah, it certainly looked a lot bigger than 1,200 square feet, so I think you succeeded with the design choices. Back to Chicago, a question from Glenn, who asked if you considered exterior shading for the large south-facing window.
Oh, you can take this side here if you want to.
Oh, I was just you can go ahead.
All right, yeah. So a majority of the shading scheme that we considered when designing for the large south-facing windows was the overhangs of the balcony and the roof. Those were specifically designed so that in the summertime, the higher sun angle would sort of interact with the roof in such a way that the large southern-facing windows would be completely shaded by the roof or the balcony above. Whereas in the winter months, when the sun angle was lower, there'd be more sunlight penetration, and this could actually help warm up the home. In terms of specific exterior shading as a more of an active strategy for shading, that is something that we did consider but opted to not use in the end, just because looking at the quality of our windows and with the shading options we already had, we figured that the benefits would not necessarily be great enough to justify the additional costs.
Very good, thank you. A question for all the teams from Trevor, who asked if you studied how long the homes can retain a livable internal air temperature without electricity and how the houses perform. So I believe that is passive survivability, if I'm not mistaken, the official term for that. But did any of you all investigate that?
So we did look into how much how often the house can get powered straight from its solar panels without needing grid support. We did not do a quantitative analysis in terms of how long the house can last with the thermally without like a grid support or with the solar panels. But yeah, that would definitely be something that we'd look into in further work, because although we know we have a really airtight and super insulated envelope, we didn't do a quantitative assessment of it can maintain within 50 or 70 degrees Fahrenheit for 8 hours or something. So that's definitely something we'd look into in the future.
Thank you very much.
I can chime in for Colorado.
Yes, please do.
Sure. So you can still hear me. We did not do a quantitative analysis, and I have to be honest, I'm not 100% sure I know what that metric or analysis would look like, but what I can say that we considered is our zoning and sort of where our wet core would be, making sure we try to maintain that wet core, and then we have insulated pipes in the crawl space, insulated hot water, and just trying to locate things so that in terms of aside from occupant comfort, just that the systems would be as safe as they can as the temperature floats.
Thank you both. And I think we've got time for maybe one last question before I turn it back over to Jonathan to close us out for the day as we approach the top of the hour. Question from Liz, who asks, Hannah, if you could address the choice of insulation, i.e. why wool and rock wool as opposed to cellulose or foam? If the house were mass-produced, how would choices and costs change?
So I'll address the insulation question first. We chose wool because we chose the sheep's wool because we really wanted to consider the embodied carbon, and actually initially very early on in the design we were exploring SIPs, structurally insulated panels, and due to the high embodied carbon of that foam insulation that SIPs contain, we didn't want to go in that direction, and also the prefabricated wall panel construction that involves the framing, so that's not SIPs, even though SIPs is prefabricated in its own way. But for replicability, we think that this panelized construction method is really kind of the main driver of the home's replicability, and we achieved really high R values with the materials that we did use, and we used the 2x8 framing structure so that we could put more insulation in the cavity and achieve those higher R values. But I guess theoretically, you could use that same construction method with a different type of insulation and it would still work as long as you were aiming for those high R values. But due to the LCA considerations and wanting to lower that embodied carbon, and also the sheep's wool has a lot of really great properties with moisture. It can dry out really well, and it's antimicrobial naturally. So those are all benefits of that.
Thank you very much, Hannah, and thank you to all of the teams and presenters today. Thank you to our audience for their questions. With the remaining 2 minutes, I will turn it back over to our MC, Jonathan, to lead us out for the day. Jonathan?
You're muted. You're muted.
Yeah, Jonathan, we cannot hear you.
I warned them of not doing exactly what I just did. See, I told you it happens even to the Secretary of Energy, and I am no exception. And that is to unmute when it is your time to talk. So thank you so much for that. And I will now repeat what only I heard, which is thank you everybody for those fantastic questions for our participating teams today. It was a very engaging discussion, and thank you to my colleague Tyler. And also, most of all, really thank you to our winning teams. It is absolutely a privilege and an honor to be able to work with such fantastic participants, and it gives us great pleasure to be able to put all the work that goes into the Solar Decathlon, and there are quite a lot of moving parts, to give the opportunity to student teams like yourselves. And you are the best of the best, and that's why we had you on today's program. So thank you so much for all of your work on the winning teams. We wish you nothing but the best in your careers, and we know that the clean energy field is better with your participation in it. So with that, we do encourage you to go to the Solar Decathlon website to see the other virtual sessions and to stay tuned for future efforts as we progress in the Solar Decathlon's work in the coming months. So that will close today's program. Thank you all very much and have a great day. Take care, everybody.